Let's take a quick look at how to use the confidence interval to calculate the confidence interval of a predicted effect. So let's go back to our normal regression, our standard example regression, where we have test scores of school districts as the outcome variable and the student-teacher ratio, STR, as the explanatory variable, and the student-teacher ratio has a negative effect on test scores. The higher the student-teacher ratio, the lower our test score, so we have this negative slope, and the slope is minus 2.28, and we have a standard error that we estimate of 1.10. Remember the coefficient, beta 1 hat, divided by the standard error of beta 1 hat is the t-stat. So in this case the t-stat is a little bit bigger than 2, so we would reject the null hypothesis that the coefficient is equal to 0. Remember also that the confidence interval of the estimated coefficient of beta 1 hat is equal to, on the lower end side, it's minus 2.28 minus the standard error, which is 1.1, times 1.96. And on the higher end, it's minus 2.28 plus 1.1 times 1.96. So we see that if we multiply 1.96 times 1.1, we have a number of about equal to 2, right? So minus 2.28 plus 2 will be about minus 0.28, right? So it's some very small number. But it doesn't include 0. The confidence interval doesn't include 0. Now we want to ask the question, what is the effect of changing the student-teacher ratio? So we have our predicted test score hat is equal to 698 minus 2.28 times our student-teacher ratio. If student-teacher ratio increases by 1, if student-teacher ratio goes up by 1, then the test score declines by 2.28. So we usually write that as saying the change in the test score divided by the change in the student-teacher ratio is equal to negative 2.28. We could also write that as the change in the test score ratio, change in the test score for 2-unit increase in STR is associated then with a decrease in the test score, and that would be minus 4.56, 2 times 2.28. But that's our estimate of the effect of a 2-unit change, but it's not the confidence interval for the 2-unit change. But the confidence interval, we can construct that because we know that at most for a 1-unit change, the decline in test score would be minus 2.28 minus 1.1 times 1.96, so at the lower end. So we can ask ourselves, that's for a 1-unit change. What about for a 2-unit change? Well, it's just going to be 2 times that. So at the lower end, we'd have minus 2.28 times 2 minus 1.1 times 1.96 times 2. So we multiply the coefficient and the range of the values in which we think might be possible or probable by 2, and at the upper end we have minus 2.28 times 2 plus 1.1 times 1.96 times 2. So that would be our lower limit and upper limit. So we can do those calculations. And when we do those calculations, this is what we get. The confidence interval for an effect of changing the student-teacher ratio equal to 2 goes from negative 4.4 to negative 0.124. So the effect would be as big as -4 if we increase the student-teacher ratio by 2, or the effect could be very minuscule, right? Still negative effect, but not very big at all for the effect on the test score. So that's how we'd calculate a confidence interval for a change in the x variable that was not equal to 1. Pretty straightforward application.